بسم الله الرحمن الرحيم. الصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. السلام عليكم everyone. Today inshallah will be finally the last lecture on the dynamics. So hopefully you're gonna be happy with that. So today inshallah everything will fall apart. Not fall apart, will fall together, sorry. Okay. So, what will happen is that we're gonna see how everything we discuss fits in the end together to describe the dynamics of general N-link manipulators. This is also easily, okay, between quotes, extendable also to floating-based manipulators, but we're gonna delay the discussion later on, okay, so that we don't have too much dynamics. So we're gonna come back to the floating-based manipulators at the end of the course, inshallah. But for now, we're gonna show you how all of the tools in the end will allow us to describe the starting point for control. Okay, so again, so don't forget we're in a control course. Okay, we spent more of half of the course on the modeling because we want to do model-based control. If you don't have a model, you cannot do model-based control. So doing modeling is part of the control. So you can think of it this way. Also, understanding the model is very important for the control because you're going to see later on the controllers we're going to be dealing with are very simple in the sense that they use the model and they just play around with the inherent properties in the equations. And you're going to see that when we do control, there are no tricks. It's just what's in the dynamics, what the properties of the dynamic model. And we're just exploiting that to design the controller. And this is the whole point. Let's start with a recap of what we discussed last time. So the building block of what we discussed here was this parent-child model where you have two rigid bodies interconnected together by some joint, by some ideal joint, which means that there is no energy loss. This is just a transformation between three inputs and three outputs. The three inputs were the twist of the parent and the reaction wrench of the parent on the child and the joint velocity, the joint angular velocity, which in this case, we assume it's 1 degree of freedom joint. The outputs of this map were the reaction wrench of the child on the parent, the child twist, and the torque that comes from the joint. So we assume that this is a joint that's actuated. So it means that this torque is applied by an electric motor. So this is what we'll be using later on for the control, inshallah. So just as a preview, the control process or the control law will be what is the tau that will make this rigid body do something that we want. Okay. So now we have two rigid bodies, so we need to think about it. So this is only a building block, and then we saw that the dynamics of the parent are given by the forward dynamics of one rigid body, and we discussed that in details earlier. And the child dynamics are given by the inverse rigid body dynamics, just because of the fact that because of this interconnection, because of this joint, then the twist velocity of the child, so the twist of the child is set by the velocity of the joint and the parent twist. And we wrote these equations in a recursive manner. So this is known as the Newton-Euler inverse dynamics algorithm. And it consists of some forward iteration that start by first the forward kinematics. And we said the forward kinematics here, this should be familiar with to everyone, where this is simply just the Brocket, the exponential formula. And then this is the equation of the twist of the next joint or of the ith link. And then we have the angular, the rate of change of this twist, and we said it has a nice closed form solution or closed form expression that we derived last time. And then in the backward iteration, we calculate the wrench that comes from the n link to the n-1, from the n-1 to the n-2, and so on until you reach the reaction from the first link to the base, to the stationary base. And we have here, these are the torques that are related to the wrenches in this way. And then if we eliminate all of the intermediate wrenches, all of the intermediate twists, and all of the intermediate rate of change of the twists, in the end, we can show that the equations will pop up in this form that is the popular. This is the starting point for manipulator dynamics, where we have the control torques or the input torques are given by some mass matrix multiplied by the angular velocities of the joints, plus some matrix that's contains a lot of the gyroscopic terms, the Coriolis term, the centripetal term. So this is a nonlinear term, nonlinear matrix that has all of the cross couplings between all of the links together. When we discussed one link, when we discussed the simple pendulum, this term did not exist because it's just because when you have several links. In general, this is a two-link manipulator. You're going to have here the coupling between link 1 and link 2, and then you have it's multiplied by the angular velocities. This is the case we derived last time, how the M looks like and how the C looks like, given that we have a two-link manipulator. What we did last time is easily extendable to n rigid bodies, okay, to n-link manipulator. And this is what I'm going to show you right now, which is also a revision of what they did last time. So I showed you last time how you can write the equations, all of them together in this compact form. We can have the V here is the combination of all of the twists. So V1 and V2 and V3, so up to Vn. And when we're talking here about the body twist, so the body twist of link 1, which is V1 with respect to 0 expressed in 1, the body twist of link n, which is Vn with respect to 0 expressed in the n frame. We had an L matrix that we derived last time, and we had some S matrix, and this was I'm going to show you, remind you now of what it was. So we have the V, we have the theta dot, we have the V dot, we have the theta double dot, we have the W, which is the collection of all of the wrenches, as you see here. And in the end, we have the torques, which are a bunch of the control torques, N torques for an N-link manipulator, assuming it's fully activated, assuming that we're activating all joints. The S's looks like this. It's just a block diagonal matrix of all of the screw axes of the joints. So you just define the joint. You look at the how many joints that you have. You look at the screw axis of each joint, and each joint. So, for example, the first joint connects body 1 with respect to 0. The second joint will connect 2 to 1. Third joint will connect 3 to 2, and so on until n and n minus 1. And you define all of these twists in the 1 frame or the 0 frame, and we saw last time that you can easily transform between them because you just have a constant transformation between them. This is the collection of all of the S's, all of the screws. This is the collection of all of the inertia matrices, the generalized inertia matrices that had the moment of inertia, the rotational inertia, and also the masses. We assumed here, just for simplicity, just to make things easier, that we put all of the frames at the center of mass. Did we have a figure here? Yeah. So we put all of the frames at the center of mass aligned in any direction. So we don't require them to be aligned in any way. So in general, we can have that I will have on the top left corner, it will have a J part. The off diagonal parts will be 0. And on the lower right corner, you're going to have M multiplied by the identity in 3 dimensions. And you collect all of these. We had here some matrices that we denoted, so we just called them together. We called this matrix that was just a bunch of adjoints that add S theta dot, and we collected these terms into what was known as the add V matrix. We also had the A and the L. So the A was given by this term, and this is the expression that you see it appearing here, for example. It was also appearing in all of the terms before, but if you remember last time, we had like an identity minus the A. We brought it on this side, and then we inverted it, and then we derived the L. Okay, so if you remember from last time, we said that the L is the identity minus the A, the big A matrix, and the inverse of that. And this, because of the fact that the A matrix was nilpotent of order n, which means that if you multiply it n times by itself, you get 0. This has a nice closed form solution that looks like that. It's I minus the inverse. And that's it. These are all of the expressions and very compact. And what I showed you last time, when you combine all of this, so you go in the reverse order. So you see the tau is equal to S transpose multiplied by the W. The W is equal to this expression. The V dot is given by that expression. The V is given by this expression. Just plug in everything in one equation. You're going to get in the end that the tau is equal to one big n by n matrix multiplied by theta double dot, and another n by n matrix multiplied by the theta dot. And last time we showed you that the m is given by this expression and the c is given by that expression. Okay, the good news and everything is good news today. Okay, so this is not coming in the exam. Okay, but you definitely need that for, maybe you need that in your project. Okay, so this is very important for a project because this is what you're going to be simulating. If you're going to be doing the simulation yourself, I'm gonna discuss that point in the end, inshallah. Okay. You mean the whole lecture? Yeah, the whole lecture is not coming. Okay. Okay. Because this is n links, and I'm gonna show you some extensions later on. Okay. Later on, when you want to do control, when you want to start with your thesis, with any project, with real work, this is the starting point. Okay. So you cannot start reading a paper if you don't understand all of the equations we're going to be talking about today. That's why I consider this to be, if you need them, you're going to come back to this lecture and hopefully understand it. It's very hard to test you in the exam for that. There will be a very nice assignment in the Ramadan break so that you can practice with. Okay, there's no free lunch. Okay, what? In the project, I'm gonna come back to that. I'm gonna show you now how to implement this in code. And if you want to do it in the project, it's possible. And then you're gonna have full freedom and full understanding of this lecture and this technique. But there are a lot of tools that already implement that for you. And that's why you can, when you're working in a project, you can just jump this step. For example, if you're, okay, not that part. So that's just a spoiler. So if you use, for example, Gazebo to build your robot and you had your RDF file for that, then Gazebo will be building all of these equations for you, and they're going to be implementing it for you numerically. If you have, for example, Simscape, in MATLAB, it does the same for you if you use Simulink and Simscape. If you're using the MATLAB robotics toolbox, they also have this implemented for you. Okay? And I'm going to show you now how it's very easy to implement this in code. Okay? Really very easy. Okay, this is how it is. Okay, these are just really a bunch of lines of very compact way. Okay, and if you look at them, you're going to find they are one-to-one to all of the expressions that we had here. So this is the MATLAB implementation of the two-link dynamics. Okay, this is a code that in the end will derive for us what the M looks like and what the C looks like. Okay, so it will not do any simulation. It will just derive for us what the M is in general, so as a function of theta, and the C as a function of theta and theta dot. In MATLAB, so we're going to use here the MATLAB symbolic toolbox. Who's not familiar with the MATLAB symbolic toolbox? Everyone is familiar? Very good. Symbolic toolbox of MATLAB. No? Okay. So if I want to have theta here so remember, MATLAB is a calculator. It's a very fancy calculator. So it does number crunching. So you give it numbers and it will calculate it for you. But it has also another feature that it can do expressions. So, and this means that I'm going to have a matrix that's a 2x2 matrix as a function of L and L1 and L2 and theta 1 and theta 2 and so on, and the mass and so on and so forth. So to do that, you use this expression. You say that I have sims. So I need to define the symbols. And theta, and I define here theta 1 and theta 2 by these expressions. So th1 is theta 1, th2 is theta 2. Unfortunately, MATLAB, as far as I know, doesn't allow you to write like nice symbols for that. Mathematica allows you to do that. Okay, so if you want to have a fancy way of doing it, Mathematica is perfect for that because it allows you to write these expressions as theta, actually theta, right? You can write theta, and does also the symbolic processing unit of Mathematica is much more powerful than MATLAB, as far as I know. In these two expressions, we define the S1 with respect to 0 expressed in 1, S2 with respect to 1 expressed in 2, which these are the joints, so the joint screws that we have. And we transform them from S1 1 with respect to 0 expressed in 0 and 2 with respect to 1 expressed in 1. Why is that? Because these are much easier to put. Okay, so in the code, whenever you have in the code, these are much easier to get just by visual, and you can just transform it in this way. I'm going to show you in the end how these look like for some examples. And here, this is the exponential formula. Okay, so this is h1 with respect to 0 home, and this is like h1 with respect to 0 when all of the angles were 0, and multiply by the exponential map. So this is the exponential in SE3. Part of the assignment is that you're going to implement this function yourself. Okay? So you're going to testing and see whether you can implement this function for yourself and see whether you actually get the final solution, the correct one or not. You're going to have a lot of fun in the break. Then we have the recursive dynamics algorithm, which is given by all of the, yes. When you say it's real, okay, so in symbolic, when you start to doing calculations and you start looking at the, want to take the transpose and so on, if you don't tell the symbolic toolbox that it's a real, it will assume it's a complex for general. And then it will start, when you do transpose, it will take the complex conjugate and so on. Okay, so when you tell it it's for real, okay, then it takes that into account. Simplifies the expressions. The S here, you define it by the block diagonal of all of these terms. The I is the block diagonal of these two expressions. The A theta is given by that term. The L theta is given by this term. And you see everything here is nothing than just that joint. That joint here is also implemented. Okay, so you can implement it for yourself. It's very easy. Or you can find that a lot of people already implemented it. In this implementation, I'm using the MATLAB implementation of the book, so the Modern Robotics book. Here I define theta 1 dot and theta 2 dot. And then I define the matrices that was the add S theta dot, which is this one and that one. So I define these two here. So these are the add and the add. All of these are huge matrices. Okay, you're gonna have this code. You can look at it for yourself, and you see these are huge matrices. If you remember, go back a little bit. So this one, for example, was 6n by 6n. So for this two-link manipulator is 12 by 12. This is 12 by 2, 12 by 12, and so on. Okay, so these are very big ones. Exactly, it implements this shape for you. So I give it only what is on the what's on the first block, and then what's on the second block and the third block, and it implements it plugs in zeros in the rest. Okay, so it's very compact way of doing it. Okay? We cannot use the same for the A theta and the L theta because you see the A theta is not block diagonal, and the L theta is also not block diagonal. It has a lot of zeros, but it's not block diagonal. So you have to implement it yourself. So in the 2D case, if you remember from last time, I had 0, 0, 0, and this was the add h1 with respect to 2 as a function of theta 2, and so on and so forth. Okay, so this is why we have these expressions there. The reduced dynamics is simply one line and the other line, so only two lines, which are implementing these two expressions here. So I calculated all of these huge matrices as symbolic, and then multiplied them together. I multiplied them together in the order that we had in the lecture. I simplify both. You get the M matrix and the C matrix. As easy as this. Let's look at what is the input here. So all of this is code. Everything from the forward kinematics, the recursive inverse dynamics, and the reduced forward dynamics, you can make it as general as possible. You can have an implementation. This is, for example, what Gazebo does, or what the MATLAB Robotics Toolbox does, is that it has an implementation for n links. And then the only thing it asks you to provide are three things. The home configuration. So what is the home configuration? All of the links that you have, which we assumed here, we put them at the center of mass, where they are when all of the angles are 0. So this is your home position. You need to define the home position. Okay, so you see these are a bunch of constant transformations. Constant r, constant psi, constant r, constant psi. Okay. They are a function of L1 and L2. I write here L1 and L2 also symbolic. Okay, so that we get everything in a symbolic way. The joint parameters of 1 with respect to 0 expressed in 0 and 2 with respect to 1 expressed in 1 are given by these numbers. Okay, they are just 0, 0, 1 and 0, 0, 0. If you go back to this example, so this implementation, okay, I'm going to show you, if there's time in the end, I'm going to show you two examples here, and you're going to have them in the MATLAB code, so you can play around with them. This is the example where you have a double pendulum, which means that you have a link, so a massless link and a ball at the end, and then you have another massless link and a ball. There's another example that you're going to have at home. We're going to have one link and another link. Okay, so the two links, the two link manipulator is different from the double pendulum. If you go back here, so this is an example of a two-link manipulator. The difference between the two-link manipulator and the double pendulum is that in the double pendulum, you have, this is massless, so it doesn't have any inertia. And you have that the center of mass is not in the center, it's at the end of the link. And the second link is the same. So this is the double pendulum. So you have a massless link and a point mass, a massless link and a point mass. But this is a two-link manipulator where the link itself has some inertia, okay, and the center of mass is in the middle. Okay. You see, the only thing that changes here are the I matrix, the inertia matrix, and where the frame is. And all of this is captured in this part. So here, these are the joint parameters, and these are the inertial parameters. This is the example of the double pendulum. So you see that the inertia is zeros. We have zeros in the top left corner. We don't have any rotational inertia. We just have m multiplied by the identity, m1 multiplied by the identity, and m2 multiplied by the identity. Okay. In the MATLAB code, you're going to derive what the m is and what the c is. And you're going to be comparing them. I'm going to give you some references where other people did it in other ways, using Euler-Lagrange, using trying to do it with standard coordinate methods, and you're going to find they're exactly the same terms. Just a little, just as a something that you might also experience yourself. So this is just a remark. Usually, the c of theta multiplied by theta dot, you can write it as another function that's at each theta and theta dot. When you compare the c, which is not this c, the new one that you got, which is the whole expression. When you compare it between different people, and of course all of them have the same dynamic, they have the correct dynamic model, they have the same, they should have the same expression. But capturing the one c out like this as a matrix and comparing the c matrices to each other is not unique. So what I'm trying to say is that I can write the c here in different ways. Okay? I can write it in a different way from another person. But in the end, when I multiply by theta dot, theta 1 dot, and theta 2 dot, and up to theta n dot, we get the same result. Okay? So This matrix is not unique, but the combination of both is unique. Okay. Long discussion. What? So I'll give you an exercise. I tell you, go read this paper that has the equations of motion for a double pendulum. You look at this C matrix that you got from this code, you find it's different from the one that they have there. Then you think, okay, there's something wrong, okay, in your derivation. But take the C matrix that you have and multiply by theta 1 and theta 2 dot. So multiply by the theta dot here. And then take the C matrix that the other person has in his or her paper, multiply by the theta dots, and you're going to find you get the same expression. Because the C here is not unique. I can write the C in different ways. Okay, I can add some term, I can minus some term, I can play around with it, but in the end, the sum is the same. Okay, so the C that we derived here in this expression, you might not find it's the same as someone else's C matrix, but in the end, when you multiply by theta dot, you get the same result. Okay, so that's the bottom line. Everything we did here, so we have first of all, how useful is this equation? Why is this the only thing that you need to simulate it? What you see down there is how you simulate it on the computer. Okay, and this is also how you simulate it in if you want to do it in Simulink. The torques here are an input. Okay, so the torques here are an input. Okay, be careful. I wrote this equation with the torque as an output and the theta dot as an input, but in the end, this is just part of how we were deriving the equations. Okay, because we were using the Newton-Euler inverse dynamics. But in the end, as an equation of motion, as a second order differential equation, this is a differential equation in theta double dot. So if you have theta double dot, you integrate it once, you get theta dot. You integrate it another time, you get theta. You take the theta and the theta double dot, you plug in back in the dynamic equation. Then you can calculate the theta double dot and so on and so forth. The only thing that's an input here is the torque. And this torque, where does it come from? From the control, exactly. So next time when we talk about control, we're going to put here another block that will output the torque and eat or like read the theta dot and the theta and so on, assuming what do you have for feedback and so on. So tau is an input. You multiply by m inverse. So if you multiply both sides by one second. Yeah, okay. So tau minus the c. So if you bring this part there, so the tau minus this expression multiplied by the m inverse will give you the theta double dot. Take the theta double dot, integrate it, you get the theta dot. Integrate it again, you get the theta, and you can calculate this term. So this is just immediately how you would implement it in Simulink. If you go to Simulink and implement this, provided that you have what the m is and what the c is, which is what you get from these expressions, you can simulate an n-link manipulator, the one that you wish for. The only thing that you need to provide, as I said, the home configuration, the joints, and the inertial parameters. Okay? So that's all for the simulation and the modeling of an n-link manipulator. We're still short of a lot of important stuff. What do you think are missing here in this expression? Gravity, external wrenches, right? Like what? What external wrenches do you think we can have? Gravity are one thing. What else? Friction, that's another thing, yeah. Friction in what? In the joints, yeah. So we can have friction in the joints. What else? The drone, we finished the model of it. Because when we had a drone, we had one rigid body. We assumed that it's just one rigid body. Each propeller produces a direct wrench on the body itself. And this wrench can be just tilted or can actively tilted or fixed tilted. And that's it. This was the whole dynamic model. So the dynamic model of drones is one rigid body and a bunch of aerodynamic wrenches on different locations. Here we have multiple rigid bodies. And then that's why we reduce them in this equation. If you have an extra torque, then it will come from here. If you have friction, it will be at the torque level. What else can have? Everything here, these are actuator stuff. These are actuator dynamics. That's right. What else? End-effector, exactly. If you have a robot arm and it starts touching stuff, where is it? If you have this robot arm and then it starts hitting on something to do interaction, this is part of what we're going to be discussing in the control part. We're not only going to be dealing with motion control, which is making this robot take some shape, but or moving from one point or doing a trajectory. We're also going to be considering that the robot would be interacting with the environment. So to interact with the environment, we need to model how this environment is acting on the robot itself. Okay. So this is the first thing we're going to have here. Let's look at how can we add an n number of external wrenches. Okay. Let's assume that we have n external wrenches. Each one of them is applied to each link that we have in the n-link manipulator. So in the two-link manipulator, in this case, I have one wrench acting on body 1 and another wrench acting on body 2, and so on and so forth. Just as a remark, wrench 1 is not necessarily acting on the center of mass. This is very important. Right? So this is my arm. If I push it in this experiment from here, or I push it from here, what is this wrench? It's the same wrench, right? So this is the wrench of my left arm or my left hand on my right arm. So whether I press here or I press there, it doesn't matter. Of course, the wrench itself, the numbers it has changes depending on what? The frame that you choose to express that wrench in, okay? So the wrench acting on the body is the same, okay? It doesn't matter where you act on it, but when you express this wrench in numbers, the numbers, when you express it in a frame, the numbers will take this transformation into account. Yes, because you're going to have an adjoint transpose. And the adjoint transpose, you see that there's a psi tilde, and the psi tilde does exactly transforms the force into torque. This is precisely what it does, yes. If we have these external wrenches, and we repeat the same inverse dynamics algorithm that we had, you're going to find that the only thing that will change is that we're going to get some external wrench here. So when we calculated here, the wrench of from the child links on each other, we're going to add here just the external wrench in this equation. And this external wrench is just a bunch of all of the external wrenches, the individual external wrenches at every link. So if I have two links, then this will be a 12-dimensional, okay, covector. Now, this is not scary. Okay, don't get scared. Okay, what will happen is that same what we did. So we're gonna multiply the S transpose, multiply by the W. So you see, and we have here an L transpose. 1 second. I think there's something wrong here. Yeah, there is definitely something wrong. There's an L transpose that's missing here. So this should be an L transpose there. Okay. Yeah. So we're gonna have here an S transpose multiplied by the L transpose multiplied by the W. Okay, so that's what you're going to have. So this is the only thing that we have here. We're going to have here what we're going to be calling a J transpose. And the J itself is nothing else than the L multiplied by the S. So if you just go back here, you're going to find this was S transpose multiplied by L transpose in this equation. So in the end, when we look at the tau, the only thing that we're going to get new is some J, this big J matrix, transpose multiplied by the W external, the wrenches external. The J here is a 6n by n matrix, so its transpose is n by 6n. So n by 6n, you get in the end n torques that correspond to all of these individual wrenches. I added here one equation. This is an extra equation. And we're going to see a lot of these equations today. These are only extra equations. We don't need them, but they will play a very important role in showing how these two parts are dual to each other. Okay. And I'm going to highlight this a lot today. So when simulating this, the first line is all what you need. But this is an extra equation, just like an output equation. Whoever took an equation course on control, for example, has this is just an aside. You have x dot is equal to f of x and u, and you also have y is equal to h of x. So y equal to h of x, this is an extra output equation. This is something similar to that. This is just an aside. Let's look closer at the J transpose, this matrix, or the J itself, because you should be familiar with it. We already know what the L is, and we already know what the S is. Let's just multiply them together and see what do we get. This is how it looks like. This is the L multiplied by the S. If you go back to the expression that we have, so this was the L, and this was the S. The S is simply a diagonal block diagonal matrix. And the L has on the diagonal identity, 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 identity. When you multiply them together, all of the identities of the L will become the corresponding S. This is what the L multiplied by S is. So this J here is simply very similar to the L, but on the diagonal here, we have all of the S's that correspond to the S. So now let's take all of this block, which is on the top, and call it J101. And take all of the second block, call it J202. These are just names. We're just introducing them. And let's take the last one and call it JN0N. This last expression, if you go back to 3-4 lectures earlier, if you already did that, or if you already you cannot do it now, but if you already studied, this should be familiar, at least I hope. This is similar to what? What? The Jacobian, exactly. We had one whole lecture on the Jacobian. If you go back, you're going to find that this expression is nothing else than the Jacobian of the end effector that we have. So the J of n with respect to 0, but expressed in n. If you go back to the earlier lectures, we expressed the Jacobian in the 0 frame. And we said that if I multiply this Jacobian by something that transforms from 0 to n, I can transform it from 0, I can have this expression. So these are all just, okay, just an aside. What I want to show you is this part here. So what I'm going to do is that I'm going to expand this expression. Okay, we already wrote it in compact. I'm going to re-expand it again to show you something very, okay, very nice here. What you see in all of these expressions is that when you remember what the Jacobian was? Does anyone remember what the Jacobian maps what to what? Theta dot. The Jacobian always maps at theta dot to a twist, right? So the theta dots, they change the whole body, right? So all of the theta dots, when you change them, the whole link will start to move, which means that all of the links will start moving. If I want to look at what is the map that goes from the theta dot, all of the theta dots, to the velocity or the generalized velocity or the twist of the first link, I can use this expression. If I want to look at the second link alone, I can use this expression. If I want to look at the last link alone, I can use this expression. Usually the last link is the most important one. Why? Because it has the end effector. But in general, you can have also, you can be interested in intermediate links. Okay, and I'll give an example in a second. But what happens very nicely with this expression is that it's transposed, the dual of this expression. You see what happens there? They are precisely the extra torques that come, the external torques that enter the dynamic equation. Okay. So all of these expressions, so if I have an external wrench that acts on link 1, it will enter with the Jacobian transpose of how theta dot is mapped to the twist of link 1. If I have an end effector wrench, something that pushes the end effector, pushes the last link, which includes the end effector, and then it will enter here. It will be transformed into torque by the transpose of the Jacobian that relates the theta dot to the end effector twist, and so on and so forth. This duality is very important. This is usually overlooked in a lot of robotics and a lot of science in general. Okay? But I like to keep it explicit because it shows you a lot of what's going on in between. Let me show you. Okay. Let me give you an immediate example why this is important. How do we add gravity now? Okay. So gravity is simply an external wrench on link 1, another external wrench on link 2, another external wrench on link 3, and so on and so forth. How does the gravity look like? What does gravity look like? It's just a force downwards, okay, that has an mg. Okay, so it has the mass of the link multiplied by some gravitational constant, and so on and so forth. So here you see, if I have the gravity acting on the first link expressed in the first frame, the gravity acting on the second link expressed in the second frame, and so on and so forth. And each one of these expressions is given by this term. And you see here, why do we have to multiply here by the r? Can anyone guess? Why isn't it this mg directly? The gyr, when you say that the gravity is downwards, this is in which frame? In the stationary frame. What is the numbers that you specify? Is it 0, 0, 1, or 0, 0 minus g, or 0, 0 plus g, or 0 g minus 0? Depending on your choice of reference frame, depending on this one. In general, for example, in drones, when you work with UAVs, there are two standard frames. One is called the ENU, is the east, north, up. And in this frame, gravity will be downwards, so it will be 0, 0 minus g. There's another frame that's also popular, is the NED, is the north, east, down. can have a frame that looks like this. North, east, down. In this frame, gravity will be 0, 0, positive G. Okay. So this is why G in the zero frame, okay, will depend on how you represent, how you choose the zero frame. But the R here will always rotate this frame, or will always rotate this downward force into the body frame that you choose. Okay, because this body changes all the time. And in the end, you just have here the mass of the ith link. And there's here the Jacobian transpose, of course, because this Jacobian will take into account, will transform this, again, with some adjoint and so on and so forth, into a torque. So in the end, this will transform this force into a torque. This is all of what you have here. All what you have here in this expression is what you do when you took in any classic dynamics course, when you take this force and then you multiply by the perpendicular distance to transform it into a torque. So this force multiplied by a perpendicular distance, you get a torque. This is what the Jacobian does. This force multiplied by this perpendicular distance and this perpendicular distance, I get another torque, and so on and so forth. This is all of the torques and the n links. So this is tau 1, tau 2, up to tau n. Okay. The Jacobian here, if you go back, each one of these Jacobians is n to 6. So the Jacobian transpose is 6 by n. It transforms something that's in 6 to n. Okay, so this J transpose multiplied by 6, it gets an n covector, which are the n torques that correspond to this wrench, and the n torques that correspond to that wrench, and so on and so forth. Okay.
Like you have a wrench and distance, so you get the torque, for example.
Yes.
Jacobian here shows like expressed at the distance, like it's a map between theta dot and
that joint. That joint has distance, and distance with a tilde, right? Psi tilde. The psi tilde, what does it do? It transforms a force into a torque, because it's the cross product. So when you multiply the psi tilde by something, if you multiply by a force, this is precisely the cross product of the psi to the force, which gives you a torque in the end. And it takes care of all of that. The nice thing, again, this is the understanding in between. Do you need to, if you want to implement this in code, do you need to think about it? Not at all. Because you see all of this J matrix, and each one of these, we have them for free in the code. If you go back to the code here, I didn't write it here explicitly, but you can extract all of these J's, because they are inside of here. So if I take this L, multiply it by the S, okay, and then I extract the first block and I call it the Jacobian, the second block, and so on, I have them for free. So it's not an extra step. I already have all of these in my implementation. So you don't even need to think about it. Yes. This one.
I thought it's supposed to be like a bunch of S. Like
No, it's the J is L multiplied by S.
Yes.
Yes.
But then the Jacobian where we treated it the other time.
Yes.
Had like adjoint multiplied by S.
That's right.
But then it's only the last one here that has.
Because I think you're right. Yeah, I think you are right. That's absolutely correct. I think there's something here. Let me go back to this. I think I'm gonna have. I think all of the S's here will also be multiplied by this part. I guess. That's right. That's right. Yeah. Yeah. That's right. Absolutely right. Yeah. I was just in a hurry of this. Yeah, absolutely. You're absolutely right. If we go back here, let's just do a very simple test. Let's see this one. If I multiply this by the S, only the first S goes here. But when I multiply this one, the first S, so this one gets multiplied, 1 second, for column, multiply by column.
Multiply with the first, the adjoint with the first S.
Yeah, this one will multiply by the first S. Yes, exactly. So the S that was multiplied here, so the S that appears here will also appear in all of these there. And the S that appears here will appear on all of these here. The S will appear here, will appear on all of these here, and so on. And then you're going to get back the expression that we had for the Jacob. Very good point, yes. Okay. I'm going to correct this in the slide. You see this term? Usually you don't see it in papers. There's a much more popular expression, which is the G term, okay? So usually all of these expressions for the gravity, they're just collected into one N vector, and they call it the gravity, the torques due to gravity, okay? So the gravity torques. So now you understand where the gravity torques come from. They're just forces on each link, transformed to torques by the Jacobian, and also they're transformed into the reference frame of the links that you have here. And again, all of this is implemented in code for you. You don't need to think about it.
The graph for link will affect the torque for link.
You mean this one? This one will act, yeah, most probably, yeah. Yeah, that's right, yeah. Yes.
The gravity for first link, it will affect for the torque for second.
Let's see. You see this one, okay, is multiplied by this gravity. Let's go to this expression. This one has two terms. So this one will be multiplied by the first wrench, and this one will be multiplied by the second wrench. So yes, so the second wrench will appear in the second equation, but also the first one will appear in the second equation. Is that what it says? No, we're looking at the transpose, sorry. We're looking at the transpose of this. So all of the wrenches will affect the last, all of the wrenches will affect the first one, and all of the wrenches except for the last one will affect the ones before, and so on and so forth. So this is the implication of this block, this triangular shape of the matrix. Think about it at home in details, okay? I haven't thought about it clearly, but I guess this is it. Yes.
Something about the initially when we started the course, you brought an expression for the transformation matrix as a semi-direct product and in the matrix form. And then you mentioned that it's more computationally efficient
Yeah.
to use the other one. Since we have a lot of zeros in our calculation here, can we also reduce a lot of these expressions into such?
That's a good point. In principle, yes. Is there an implementation that does it? I don't know. I don't know. I don't know. Why would you like to remove the zeros? Zeros are nice. Okay. Maybe you can implement this again using, for example, some structure, for example, that's triangular. Okay. There's a nice thing about actually all of this implementation that I had here is that you don't even need to have it in this matrix form. So everything that I showed you here is just for your own satisfaction, so that you can see all of the expressions together. But we already had them in a recursive way. So actually you can calculate it in a recursive way in the same way that we had them from the start. So this is much better for the computer to have it in a recursive manner. And you just have inner n loops that will just calculate the expression for you. And we don't need to have this matrix multiplication and so on. But even this matrix multiplication is not a big deal because we don't have any inverses. Okay? So this algorithm, if I remember correctly, it will be of an order n, right? So if you have 100 links, this will be an order of 100. It's not n squared and so on and so forth. The simulation is another issue because the simulation here, we have to calculate the m inverse, and the m here, calculating the inverse of this n by n matrix, this is an issue. That's why there are a lot of ways that you can discretize this more smartly or better ways, but out of the scope of this course. Let me show you something that's tricky. I'm pretty sure the first time you see it, but it's very elegant. So it's a pity that I would say it's a pity not to mention it in the course. Okay, this is how you all know how gravity works, right? Makes sense. Is there another way how gravity works? Yes. Okay. So this is Einstein's equivalence principle. Okay. So there are a lot of YouTube that you can spend a lot of time here. So that, again, you can do it in the Ramadan break. You can watch a lot of YouTube videos on how this works. But the idea is the following. This is Einstein's equivalence principle, and it's stated as boldly as this. There is no local experiment that can distinguish a uniform gravitational field from an accelerating reference frame. Right? And the example is the following. This is the standard example. This is from Wikipedia. I take this, what Newton did. So he took the apple and he threw it, it fell down. Okay. So this is this picture. Now take Newton and put him in a spacecraft that's accelerating. away from any gravitational field, away from any planet. And the acceleration of the space of the rocket itself will make, when he leaves the apple from his hand, what will happen to it? It will fall to the ground. Or in other words, the ground will come up to it. Okay? So in this example, the ground will come up, but in this example, the apple will go down to the ground. And these two experiments, they are exactly the same. Nothing in the math says that you either have this one or that one. So the math of both experiments is the same. Newton's law in both equations, okay, or how gravity works in both equations is equivalent. So all physical laws, so this is the statement, again, this is the consequence of that, is that all physical laws in a freely falling laboratory, or in our case is a reference frame, take the same form as in an inertial frame with no gravity. Okay. What is the equivalence of that? There is a much elegant way that you can calculate this gravity torque. Okay. Again, there's an S transpose, L transpose. So you see there's some Jacobian there, transpose. There's an inertia tensor, so the mass goes into place here. There's again some L, so L transpose, and I. But in the end, we have here some acceleration. This is the acceleration of the world. So instead of assuming that we have the frame is stationary and gravity is pushing, okay, is pulling all of the links down, we're going to assume that the whole setup is falling down. Okay, free falling in gravity with no gravity, so just free falling. If you have something that's free falling downwards, what is how does this person see the world? Again, if imagine yourself, okay, you jump from a mountain. We don't try that at home, okay? So you imagine yourself, you're jumping from a mountain, and then you look at the world. The world will be moving up, okay? And your reference frame, in your observer, you're going to be seeing all of the world going up. So if you always consider gravity to be in the zero frame to be, for example, going downwards, the acceleration of the reference frame, of the zero reference frame, you can consider to be up, okay, with minus this gravity. Okay, so if this was minus g, okay, in the third direction, in the z direction or in the y direction, this will be positive g in the y direction or in the z direction. Multiply this term by this expression, you're going to get the gravity. That's it. Okay. There is no experiment that you can think of or you can do that you can prove that these are the two, okay, this is equivalent to getting the gravity. The only thing that you can do, calculate this expression, compare it to this expression, you're going to get exactly the same terms. And this expression is, again, we have everything there for free, right? We have this term, we have this term, we have this term. We just multiply them in this order by this very nice looking vector. Everything will work out. You're going to get precisely the gravity vector that you have. Okay.
So is it reasonable to then say that for the body frame and the reference frame, in reality, the body frame could be the stationary one, and the reference frame could, quote unquote, be the one accelerating or moving?
This is what we're doing here. Yeah, this is exactly that. So the zero frame is accelerating, and everything here is fixed with respect to that. Okay. So this is the stationary part. Yeah, that's correct. Last part. I think that's the last slide. Okay, so last slide. That's it. Not yet. Wait. Okay, so the last slide is what happens when we have an end-effector now. So the end-effector is usually the tip of the last link. So if you have a two-link manipulator or an n-link manipulator, the tip of it is usually where you're going to have the end-effector. So we're going to have here, there's usually a standard way of defining this range. So usually it's defined usually in a lot of places that this is the range applied to the environment by the end-effector. To the environment by the end-effector. If you go back to these expressions that we had here, there was a minus sign here. Why is there a minus sign here? And why is here? And why do we have here a plus sign? What's the difference?
Environment on the tip.
Exactly. Exactly. So Newton's third law, okay, both are same magnitude but opposite direction. So the end effector, so the range acting that that the end effector does on the environment is minus the wrench done by the environment on the end effector. The expression that we have here with the minus sign, if you go back here, are oral or external wrenches applied on the link. That's why we have here a minus sign. But these are the wrenches applied. This is the wrench applied by the robot, by the robot's end effector to the environment, to whatever there's out there. Okay, this is the robot arm, and you have the environment, which is we don't know what's there. It can be anything. This is open. We're gonna have here some Jacobian. Again, there will be some Jacobian matrix that will transform this to some torques. And we're gonna have here the corresponding twist that's dual to that. How is this J matrix, this J end effector defined? First, it's going to have the J2, the Jn part, which is this expression, that the last one that we had here. So this one, because this is part of the last link, okay, the N link. But if you look here, the N link is not, so where the frame of the N link is not the same usually as where the end effector is in general. And this is why you can have a constant transformation. It will transform the center of mass of the last link to the tip. Okay. So you see here, we're going to have here some adjoint that will transform the two twist to the E twist. Now a question to you. VE with respect to 0 expressed in E. Why is it equal V2 with respect to 0 expressed in 2 multiplied by the adjoint directly? Why don't we have any extra term here? Exactly. Both of them are body fixed. So 2 and E are body fixed. So the relative twist between 2 and E is 0. We had that in the assignment many times. So 2 with respect to 0, the relative twist is 0. So the twist of this one is the twist of that one, just expressed in a different frame. So 2 with respect to 0 expressed in 2 is the same as E with respect to 0 expressed in 2. So if I want to transform E with respect to 0 expressed in 2 to E with respect to 0 expressed in E, I just multiply by 2 to E. The transform of that, so the transpose of that, the dual of this transformation, will transform whatever end effector twist it sees, whatever wrench the end effector sees at its point or at the tip, it will transform it by the add transpose to the 2 link, okay, to the center of mass frame. And then I transform it by the Jacobian transpose to some torque that enters the equation. Okay? So this expression you're going to be seeing all over the place in any paper that works with robotics that has some interaction. You're always going to see this expression. And they just say this is a Jacobian without proving how it looks like. And this is how it looks like in what we discussed. Okay? And again, you know all of these terms, how you can derive them, how you can expand them depending on the scenario that you have you're thinking of. So that's it. So now you see in the end, the manipulator equation is an equation in theta double dot that has as an input tau. It has here as an input also the wrench, any external wrench that you have. If you have here gravity, you're going to add here the gravity terms. If you have interaction not with the end effector, for example, if you have what's known as collaborative robotics, okay, so co-robots, if you have a co-robot, then this robot, I can touch it also on the hand, right? Or I can touch it here, right? So, for example, I might do manipulation by pushing this bag like this, not just with my end effector. So I can, in principle, I can interact with any of these links, right? With any of my links. What is the corresponding, how the corresponding equation will change? You just go back to this expression and you look at it and just transform any one of these, depending on which one you're interacting with, okay? So if you have a robot that interacts with multiple links, it has multiple contact points, it's easily extendable to this case. One last thing to say, maybe that's a little bit, maybe it's interesting, maybe it's not, is this expression. We assumed here that all of the joints are actuated, right? So here I assumed all of the joints are actuated. What if we have some of the joints are not actuated? What changes here? No, not that. Okay. What changes here? What? Exactly, that their corresponding torques will be 0. Okay. So what you're going to have here, instead of the taus, you're going to have here some sort of matrix. It's called a selection matrix. The selection matrix will select which one of these torques is actually actuated and which one is 0. And you're going to have here this S transpose, this matrix, the selection matrix transposed. You're going to have here also its corresponding S multiplied by the theta dot. It will specify which joints are actuated, which degrees of freedom are actually free to rotate by themselves, and which ones are not. So again, you're going to have also the duality here. This expression, what I just mentioned, is very important for people who work in quadrupeds. So whenever you have a quadruped and you see the dynamic equation of motion, you're going to see directly this expression that you're going to have here a selection matrix. If you have anyone is familiar with what's known as the acrobot, there's a double pendulum. So there's a double pendulum that has a motor on the first joint, but no motor on the second joint. So it's an inverted pendulum. It's a double inverted pendulum where you have only 1 degree of freedom to actuate. But still, it's a 2 degree of freedom system, but only one of them is actuated. So this is an underactuated system. Usually, it's like standard when you study underactuated control and so on. This is known as the acrobot. Okay? This is like a toy problem for underactuated system. That's it. So, yeah.
The second link would be free to rotate.
Yeah. So you rotate this one, and because of the dynamics here, the second one will start to rotate with. Okay.
Sometimes it on itself.
Exactly. And this acrobot, for example, if you do any reinforcement learning, this is also a standard problem because this is more interesting because it has all of these internal dynamics and how can we actuate here one link and make it, for example, this inverted pendulum to stay up in the air. Okay. So this is a standard problem. Okay. So this is if you have the equation.
For example, actuator in a link, but there is, for example, a worm gear or something to keep it stabilized. Will this have effect on the core, or it will be as an external wrench by, for example, friction or something?
Here. All of the you see all of these part, it goes here to the motor. Anything that you have to do any dynamics that you have at the motor level, so for example, gearing, friction, if you have inertia of, for example, of the gears, which is the part of the gearing, if you have backlash, for example, if you have some dead zone due to backlash, all of these will be dynamics that you include here. And these are known as actuator dynamics. These are only the rigid body dynamics that we discussed, but usually the actuator dynamics are, in some cases, more complicated than actually the rigid body dynamics. And they have a lot of implications on this. There's a very nice part in the book, in the last section, or the section, one of the last sections that we didn't cover in the book, chapter 8, you're going to find that it discusses this actuation and the friction and the gearing and so on. It's a very interesting one. Okay. Yes. If you have friction here, it will go there even if you don't have any actuation. Okay. So if I put directly here some actuation, some friction, there will be no. All of these expressions will be the same. You're just going to have here some matrix multiplied by theta dot, theta 1 dot, and theta 2 dot. Just like when you have one pendulum and you say I have friction, you just multiply by some damping friction and multiply by theta dot. So B theta dot and so on. You're going to have here also a B matrix multiplied by theta 1 dot and theta 2 dot and so on and so forth. Okay. There's a lot that you can extend this with.
The selective matrix multiplied by the top, the same control allocation matrix.
Is it the control allocation matrix? It's the control input. I would say it's the control input, which is, yeah, you can think of it as a control allocation, yeah. But it's already, it doesn't have any degree, it is the control allocation. Yeah, I would say that's right. Yeah, the same as the control allocation. Any more questions?
Sorry, sir.
Yeah.
The control allocation, isn't that what we treated when we were dealing with calculators?
That's right.
But then we mentioned that it's supposed to be the inverse of the transpose of the Jacobian.
Yes.
But then we're already dealing with the Jacobian here.
What we did there is that we didn't derive the control allocation using a static wrench analysis. So directly as a wrench, we didn't derive it as the transpose of some Jacobian that released the theta dot to the bodies. You can do it and you're gonna get the same result. We didn't do that. Okay, that's why it's related to the Jacobian, but it's not clear at the first sight what it is.
Then when we it's been similar to that, the control allocation, then we also have a Jacobian transpose.
No, it's the control allocation in this problem. No. So it has nothing to do with that control allocation matrix. It's the control allocation of this problem. When you have here a selection that specifies how many torques are actuated and how many are not. This is just
It's not connected to Jacobian.
Not related. No, it's not related to the Jacobian. No. Any more questions? Enough? Okay. So that's it. So that's the dynamics. So now you should be able to model any n-link manipulator. Okay? So if you have an n-link manipulator in the project, okay, good luck with that. If you have the quad rotor, you already can do that. So we already covered that. If you have a multi-rotary AV, you already can do that. If you have a floating base manipulator, you can extend this approach to the floating base manipulator, but you're just gonna have some extra studying to do. Okay, so if you have that in your project, do this extra homework, or if you want to do that, if you want to understand the dynamic modeling, or just wait until we cover it in the last topic of this course. Okay, and it will be too late also to work on the project by then. But that anyhow. Okay.